I have your exams. At least I got that accomplished during spring break. I'll post the answer key sometime later today. But I'll give you those after class. You can take a look at them. The scores are in. I just have to unmute the grades, and then it'll update your scores. Midterm grades are due on Wednesday, so those will be the basis of the midterm grade. And I think I'll be giving everybody a midterm grade this time, because that's the way we're moving. Okay. So what I want to do is I'll probably be lecturing most of the week. I know I will today and Wednesday. So these are the notes that I'm going to use to talk about reactions of benzene rings. So the first thing that we have to do is we have to talk about reactions outside of the benzene ring, and then we'll talk about adding things into the benzene ring and all that goes with that. So in terms of just some quick naming, because I don't remember last semester how much naming we did. Basically, the benzene ring itself is benzene, but then as you add different things to it, the name changes. So a methyl group is toluene. Anything above a methyl group, an ethyl or propyl, would just be the common name of this group plus the benzene name. There are some substituents that have a particular name, though, like phenol. Two methyl groups are xylenes, and you could have an ortho, a meta, or a paraxylene, and we're going to use those terms in the coming week. The OCH3 is not methoxybenzene, but it's called anisole. And then there's aniline with an NH2. And then whenever you have a CH2 attached to the ring, that's a benzyl group. So you can have things like benzyl alcohol, benzoic acid, and benzaldehyde. So in terms of the naming systems, these all become the parent names, and then you name whatever the substituents are that are attached to the ring. And we're not going to go into much more detail than that, other than you could have, for instance, a ortho, a meta, or a para benzaldehyde. So you could have like ortho methyl benzaldehyde, or basically what would be 2-methyl benzaldehyde. Every one of these groups that's listed gets the number 1 position on the ring. And so you can read through the IUPAC. We're going to start using the ortho, meta, and the para, so you have to remember that ortho is 1,2, meta is 1,3, and para is 1,4, and that's all relative to a substituent that's already on the ring. So we're going to use that ortho, meta, and para terminology, particularly when we start adding things into the ring. So let's talk about reactions of the ring. So we spent a couple weeks ago talking about how stable the benzene ring was. And so the question is, can I break up the aromaticity of the ring? And it's really difficult to do that, but it can be done. And the way that it's done is by using sodium metal in liquid ammonia. So this is our strongest of reducing reagents. So if you think about taking a sodium metal has 1 unpaired electron. When you place it in ammonia that's, again, in its liquid form, the sodium gives up its electron to form what's called a solvated electron. And so that electron then is free to add to a reagent. That reagent gets an electron, gets electrons as reduction. So this is the absolute purest form of a reducing reagent And it's the strongest reducing reagent that we can get, short of maybe taking an electrode and trying to pump in an electron. So what happens in this case is that we reduce the triple bond, we reduce the 3 double bonds down to 2 single bonds. And those 2 single bonds are always not conjugated. They're what we would call isolated. And this is what's called Birch Reduction. So the Birch Reduction will remove the aromaticity of a benzene ring. And that's the only reason we know it, because that's an incredibly difficult thing to do. If you wanted to go through the mechanism of this, you can look at it this way. In terms of adding the unpaired electron, these should all be half arrows, but apparently I didn't have access to half arrows in the drawing program. So you can see how the electrons might move. If you were to go back to the beginning of the semester and remember how when we took a triple bond, when we added sodium metal and liquid ammonia to a triple bond, we ended up reducing that triple bond into the trans double bond. I mean, I know that was a long time ago, like 3 months. But in that case, the key step was that we ended up with, in the double bond, a lone pair of electrons on one end and an unpaired electron on the other. And because those big clouds got to be far away from each other, that is what forced the trans stereochemistry. And this is exactly what happens in the reduction of the aromatic system. You end up with an unpaired electron, a radical. The anion part is on the other side, so they always end up 1,4, or what we're going to call para disubstituted. They always end up with these 2 big clouds that have to be opposite each other. And so that's what forces then the system to become an isolated diene. And the hydrogens that are added then, the 2 hydrogens that are added are always going to be added to the 1 and the 4 positions. Okay. So I just show you this mechanism. This isn't something I'd ask you to reproduce, but if you get stuck and go, I can't quite remember that, if you just remember that in any kind of sodium liquid ammonia reaction, you're always going to end up with 2 clouds, and they have to be as far away from each other as possible. That's where the hydrogens go. Then you might be able to figure this out. Okay. So that's the Birch reduction. We end up taking the aromatic system and converting it into a isolated diene. Now you might say, what happens? And then there's the rest of the mechanism. What happens if there's an alkyl group attached to the ring? There's an alkyl group attached to the ring. The alkyl group will be attached to one of the 2 double bonds, because basically what we'd like to do is we would like to make the more stable product. And so that's what happens when it's substituted. Okay, so that's Birch reduction. And let's see, we're in chapter 20 now. And so the chapter 20, as we'll be doing these, I think I have them set up for Friday. The chapter 20 top hat problems are due on Friday. Again, maybe you could finish them up over the weekend if I don't jump on the score right away, which you saw what I did in chapter 18, so you might have the weekend. But if you want to keep up, this is the perfect time to kind of do it as we do this stuff in lecture. Okay. Reactions at the benzylic carbon. So the benzylic carbon is special. We've kind of already seen that in terms of forming the free radical. And let me just say first, X here, that X, those X's should all be R's. X normally means halogen. That's not my intent. My intent is that they all are alkyl groups. Do you have a set of notes, Jacob? It'll be even better. So that's not a halogen, it's just simply an alkyl group. Does everybody else have a set? I think there were extras somewhere, probably. No sense in writing down stuff that's already written down for you. Okay. So the benzylic position was where we would do free radical halogenation. And just to go back and think about free radical halogenation here, when I'm using a benzene ring and I want to free radically halogenate at the benzylic position, I can use Br2 and light at room temperature, or I could use NBS. I could use either of these sets of reagents to benzylically free radically halogenate. And the reason that I can do that, because remember, you can't use Br2 and light if you just have a normal double bond, because the Br2 will add to the double bond. Okay. That was one of the test questions. And the reason I can use Br2 is because, remember, Br2 itself does not add to a benzene ring because the benzene ring is too stable. Now, if I put Br2 with something else, I'll actually be able to add the bromine to the ring, but not right now. So just Br2 itself will not add to a double bond. Sorry, it will add to a double bond. It won't add to a benzene ring. And so we can use Br2 with the benzene ring. Or we can use NBS. But that will brominate at the benzylic position exclusively. Okay. If we want to make carbocations, our carbocation at the benzylic carbon is special because we can now draw resonance structures for that. So if you wanted to, you could move that pair of electrons there, and you could put the double bond inside of the ring, and put the plus charge inside the ring. Once a plus charge goes inside the ring, there's two more resonance structures I can draw. And we'll see examples of those, and I'll probably give you a take-home quiz on Wednesday to draw all of those out. So the benzylic carbocation is stable because of all the resonance structures that it can draw. You can draw off of it. The carbanion is also stable at the benzylic position because I can do the opposite. I can take this pair of electrons and move it here, and then have that pair of electrons move out to that carbon. So I can start my resonance structure and that's the first resonance structure that I can draw. Just just going to make this bigger. Okay, so the benzylic position is where the carbocations will form, it's where the radicals will form, and it's where we would prefer to have a negative charge form as well. Now, the problem with the negative charge is that normally the way we form the negative charge is to take and have the bromine or the chlorine at that position and then add magnesium to it. And so that's how we can form the negative charge. But what happens is, how do we brominate, or how do we put the bromine at the benzylic position? We use our free radical halogenation. So the free radical halogenation puts the bromine only at the benzylic position, and then when we want to react it with magnesium and make the anion, the negative charge is that's where the negative charge is going to go. Okay. So all of our side chain reactions, what are called side chain reactions, the reactions on the chains, they're attached to the benzene ring. Not in the benzene ring yet, but on the outside, the benzylic position is going to be our favorite or special position. So in theory, if we have a carbocation formed, in theory that carbocation is going to end up on the benzylic position. So that's the important thing to keep track of in terms of the benzylic carbon. Right. Everybody okay with me? The clock's changed. There's no more fun of spring break if you had any fun. It's a tough day. Oh, and by the way, we're still having our panel discussion at 3:30. An hors d'oeuvre social. So you can come and meet some of our chemistry alumni. If you're going to be a biology major, there's going to be a biology major there too, but feel free to come and you can listen to what their jobs are. You'll get an email from Mrs. Yon. You probably already got it as a reminder. So if you're available, that's going on today as well. Okay, we did this reaction in lab last week. If you take an alkyl group, any size, we took a methyl group last week, and you oxidize it with KMNO4, you end up converting that alkyl chain, no matter how long it is, to a carboxylic acid. And so, if I remember correctly, what we did last week was we had added our C double bond OCH3 group, our acetate group. We had added to the NH2, and then we treated this molecule with KMNO4. And I know because I spent 2 hours yesterday cleaning up all the balances, because wherever there was a spot, there was a piece of potassium permanganate there. So I had to take everything, put it in the sink, and the sink was completely purple because the potassium permanganate was everywhere. And you should have, why'd you do it yesterday instead of after lab? Because I was lazy. And I wanted to wait as long as possible because I knew there would be potassium permanganate everywhere. So if you find any little purple spots on the balances, that's what it's from, but hopefully I got it all. I digress. Potassium permanganate reacted then with this methyl group, and it converted the methyl group into a carboxylic acid. So that's where we stand right now in lab. we have our carboxylic acid and our amide. And you might have, and if you're asking, like, why did we add this? Why did we add this acetate group to the nitrogen? It was to keep the nitrogen from oxidizing to an NO2 group. So you can actually convert an NH2 group to an NO2 group. And we'll talk about that reaction later on. So when we converted it to the amide, that stopped the KMNO4 from reacting with the nitrogen. So it would only react with that. Because I believe this week what we're going to do is we're going to take off that acetate group and turn it back into an NH2 group. And then when we do that, it's going to create all sorts of problems because the carboxylic acid is going to want to protonate the NH2 group. So we're going to end up with a zwitterion with an NH3 plus and a COO minus. And it's not going to want to dissolve in anything but like water. So that's what we're doing this week, at least if my memory is correct. So when you want to oxidize an alkyl group, you'll always make the benzoic acid. And if there's more than one alkyl group on the ring, you'll oxidize all the alkyl groups. Okay, so that we've already done in lab. We've already seen the consequences of that. How about SN2 reactions of benzylic halides? In general, benzylic halides react faster than other halides. Why? Well, if we go back and we draw out our transition state, which in this case would be there's the structure of our transition state. What am I missing? Where? Okay. Oops. There's one more. Right. We don't normally write the delta positive on the carbon, but in this case, it helps us explain this answer to this question. So when I put a delta positive charge on that benzylic carbon, if I add a benzene ring to that carbon, what happens? That benzene ring stabilizes that delta positive carbon the same way it would as if it was a true C+. I'm lowering the transition state energy. I'm lowering the energy of the structure. I'm making it more stable by adding this benzene ring, and therefore that's going to make the SN2 reaction go faster. So we've forgotten about that delta positive charge for a while, but in this case it explains why a benzylic halide will react faster in SN2 than a normal, actually even an allylic, because we have that stabilization. These are all side chain reactions. Oh, good. Now comes the fun. So I have a couple questions here. How could I make this molecule, which is called methylstyrene? The double bond just attached to the ring is a styrene molecule. If you've ever heard the term polystyrene, polystyrene is what makes up styrofoam. If you take it's a long chained polymer of the styrene molecule, which would be without this methyl group. And that molecule then, if you make it, these long chains, but you blow air into it or CO2, then it forms the bubbles, the plastic with the bubbles, which is styrofoam. It's not really environmentally friendly, but anymore. But we still see it around. This molecule is methylstyrene. So how could I make that from propylbenzene? Anybody have any suggestions? Should we make that a take-home quiz?
Do free radical halogenation to put something on the benzylic.
So let's start with a free radical halogenation. Of all the reactions that I know that I can do on this alkyl benzene, we just talked about one, which was KMNO4. That's not going to be helpful, right? Because I still want this propyl group to be intact. So KMNO4 is out. What other reaction do I have that I can do with a alkyl group on a benzene? Free radical halogenation. So let's say that I react this with Br2 and light. Where is the bromine going to go? To the what position? To the benzylic position. Okay? How do I get from here to here? E2 reaction. So what reagent would I use for an E2 reaction? NH2 minus? What else could I use? I could use tertiary butoxide. I'm going to write or tertiary butoxide. Will both of them work? Will just one work? Both will work. Yeah, both will work. Why? Because there are no hydrogens here, something that we have to get used to. There's no hydrogens to the left. There are hydrogens on the right beta carbon, and so it doesn't matter which base I use, it would remove that beta hydrogen and make the styrene. This double bond is in what with the ring? This double bond is in blank with that benzene ring. Starts with a C. You had it. Sort of. Conjugation. So that double bond's in conjugation with the ring. And that will be something that we will want to do where possible, is put the double bond in in conjugation with the ring. Okay. So we're going to want to think, we're in the second half of the semester now. We're going to begin to think a little bit more about, let's do reaction A, then let's do reaction B to maybe get product C or G, depending on what letter of the alphabet we're at. How about this reaction, the second reaction? Now, let's change this a little bit. And let's write, no, we haven't, HCl. Let's say I added HCl to my methylstyrene. What would be my major product? The only reason I'm changing it because we've done this reaction in the lab in the last 3 months, and so I know what the answer is. So what do you think? Where should the H go? Should the H go on carbon A or carbon B? Give me a letter. Carly?
B.
You want the H on carbon B? Anybody else want the H on carbon B? Anybody want the H on carbon A? Anybody have no idea where the H should go? Okay. So we got Markovnikov's rule here, right? That's what should dictate this. So our problem is that each of the carbons in the double bond has one hydrogen, so they're tied. So does that mean that we get a 50-50 mixture? I can tell you no. The benzene ring is going to play a role. So what we would do in this case is let's broaden Markovnikov's rule out. The H is going to add to the carbon that gives us the most stable carbocation. So what do we think that most stable carbocation is going to be? The benzylic carbocation by putting a plus charge at A, or by putting a plus charge at B, which is not benzylic. So where should the positive charge go?
A.
That's where the carbocation should go. Why? Go back like 4 slides. Right? That's our benzylic position.
This isn't 100% though, or is it?
Actually, it is.
It is 100%.
It's 100%. Like I said, we've done this reaction. This particular reaction, we did it and we got 100%. How do we know that? Take an NMR of it. And actually, it seems like HCl, adding HCl to an alkene would go like that, because on paper it looks like it takes like a week. Actually, we let it stir for a week, and it didn't go 100%. It went 100% of that product, but it didn't go 100% reaction. So then we found some other method that made it go like within 3 hours. I'm a little surprised at how unreactive alkenes are with HCl, because we always talk about them in this class as if they go instantaneously, and they don't, sadly. But if we add the H to carbon B, we get a carbocation that's benzylic, and then the Cl minus comes in, and we get actually 100% of adding the HCl that way. So in this case, what we would conclude is that a secondary benzylic carbocation is more stable than a secondary non-benzylic carbocation, is what we would conclude from that. Okay. So, in general, if I'm going to do a reaction and there's a benzylic carbocation, that benzylic carbocation will be stable. And it'll be more stable than anything else in the chain, the other possible carbocations. And what I should probably not do is say, because you'll probably see this in some of the homework problems, what if I want down here, what if I want to test the stability of a secondary benzylic versus a tertiary carbocation? Which every time I've shown this reaction, I've thought that would be a good experiment to do. And so we actually did it. And the H adds here, and the Cl adds here. So it goes by Markovnikov's rule, 100%, but the benzylic carbocation is not formed. Only the tertiary is. So I'm a little confused by that. Actually, I'm a lot confused by that. Because I would normally say, oh, secondary benzylic beats a tertiary. But in this case, the tertiary wins. And that's what Brian's working on, and that's where we're stuck. Because when we first found this, he's like, I don't believe anything you taught us in organic last year. Because I had it going the other way. And I said, well, I guess I was wrong. But we're trying to figure out why. So sometimes you do end up, these look pretty simple and straightforward, and then they're not. So then you got to figure out why. And that right now is, at least the computer's not broken so that we can do some modeling on this. The NMR still isn't fixed. But that's one of my unfinished things over break. Okay. So usually, except in this case, the benzylic carbocation is special. In this case it isn't, and I don't know why. I think I know why, but I don't have any evidence of it yet. Okay. So these are kinds of reactions. We're going to go back and we're going to do like kinetic and thermodynamic reactions, where the benzylic carbocation is going to be the most stable intermediate. So all I'm going to do is put the benzene ring in. That's going to create a benzylic position, which is going to be more stable. Okay, now let's move on to doing reactions inside of the ring. So what we've seen so far is this. Well, we haven't seen it. I've told you, assuming I'm correct, which I think I am, although after that last reaction, there is a little doubt sometimes. But I think it's well accepted that if we just add Br2, or if we just add KMNO4, or if we just add HCl, or HBr, or sulfuric acid, that if we add any of those just to a benzene ring, we get no reaction. Because the benzene ring is super stable, it's aromatic, it will not react. Okay. That's what we know to this point. So how do we add things to the benzene ring? And that's what's going to be called electrophilic aromatic substitution. Okay. So the basis of electrophilic aromatic substitution is this. I'm going to add an electrophile with a positive charge to the benzene ring. It is going to substitute for one of the hydrogens on the benzene ring, so that I end up doing a substitution reaction where basically I'm substituting with one electrophile and I'm forming H+, the other electrophile. So this is electrophilic aromatic substitution. But it's going to take a pretty harsh electrophile, like a C+ or something with a plus charge. to add to that benzene ring. So then all the different reagents we're going to use all generate a positive charge. And that's what's going to add to the benzene ring. So you could go through the mechanism of this. Usually I like to do this because it keeps people awake instead of just looking at the notes. But here's what happens. I'm going to take a double bond. I'm going to add the electrophile to it. So now I'm going to end up with that carbocation. That carbocation has two more resonance structures that I can draw. There they are. Okay, so I'm just drawing all the carbocation resonance structures inside the ring. If you're saying, wow, that looks hard, I would say erase the ring. Like, I can't do that by doing this. It doesn't show my finger. So I have to, let's see, I don't have any sticks. It's probably too high up there for me. But what I would do is do this. Oh, that doesn't even work. What was I thinking? What I need is a shadow. Now you can't see because there's books in the way. But take away half that ring. If I take away half that ring, all I've got is an allylic carbocation. So if we've been able so far to write the structure of the allylic carbocation and draw its resonance structures, we can do that with the benzene ring. We just treat it, it's an allylic carbocation. Okay. So that's what we do. And so we added the electrophile here. That put the positive charge there. The positive charge goes there. The positive charge goes there. And so in my resonance hybrid, which this one turns out to be still correct, I've got delta positive charges on those three carbons. And so that's my resonance hybrid. Now what happens is that once I form this carbocation, I'm going to lose the H+. Now let me go to the next slide because the question is, do I lose the H+ or do I, well actually no, the question is which H+ do I lose? So, or have a nucleophile attack. So here's my resonance structure. Normally what we do with the double bond is we add the electrophile and then we add a nucleophile to it. So that when we add our electrophile and our nucleophile across the double bond, that's like adding HCl, HBr, H plus H2O. That's what we've done when we've added an electrophile followed by a nucleophile. And I could do that here. I would get this product. Is that the most stable product I can get, though? No. I'll answer that. Because what can happen is that if I lose my H+ and take that pair of electrons and move it back, I now reform the double bond, and so I reform the aromatic system. So while we start by adding an electrophile to the benzene ring, we don't do what would be called electrophilic addition, because electrophilic addition would be add the electrophile, add the nucleophile to the double bond. That's not going to form the most stable product. What's going to form the most stable product is to then lose the H+ and do substitution, because that's going to reform this benzene ring. So, and that's what's going to happen. So now the question is, if I can do all of that, and you'll be able to do, well, you'll have practice in doing all of that before the next test, which isn't that far away, because it's the end of the month. How are we going how are we going to add electrophiles? All I have to do is make a positive charge. So here's the first step. You want to add an NO2 to the ring and make nitrobenzene. If you want to make nitrobenzene, what you do is you have to form an NO2 plus. How do you form an NO2 plus? Take sulfuric acid, add nitric acid to it, and what happens is you basically protonate the nitric acid. It loses water, and it forms NO2 plus. Okay. That NO2 plus is now my E plus. It adds to the ring. Is there like a speaker? Am I back in high school with announcements? Add sulfuric acid to SO3, and you just simply protonate the SO3 to make the SO3H plus. And when you add that to the benzene ring, you make a sulfonic. You make what's called benzene sulfonic acid. We'll come back to that because that is one atom away from being a tosyl chloride. You want to halogenate? We said Br2 doesn't work. But add Br2 and FeBr3 or Br2 and AlBr3. The FeBr3, for instance, will strip one of the bromines away, and now you've got a Br plus, a true Br plus, that now is strong enough to add to the benzene ring. Every one of these would have the same exact mechanism, because all I would do is use each one of these positively charged species. Every one of them is the E plus in the mechanism I just showed you. Okay. So that's what we're going to do. First is we're going to learn all the different ways to make the plus charge and add it to the ring. And when we're adding things to benzene rings, it's a piece of cake because I got 6 hydrogens. Doesn't matter which hydrogen I substitute for. It's going to be a little more complicated when something else is on the ring. When something else is on the ring, where does the E plus go? Ortho, meta, or para? And so there's a system that'll be involved there. All right. So what I have for you is I have a take-home quiz on aromaticity, since I left that off the last test, and so you can pick one of those.